Hey everyone, and welcome back to Pod 4 Journal Club. Today we're diving into a fascinating paper that gets right to the heart of one of the biggest questions in AI. What does it really mean for a machine to learn? So here's the mystery we're exploring. When an AI solves a problem, does it actually get the logic behind it? Or is it just an incredibly good mimic, a sort of expert parrot that's just repeating patterns it saw in its training data? Well, to figure this out, some researchers designed a really clever test. And the key concept we're talking about today has a bit of a fancy name, systematic generalization. But trust me, it's something you and I do all the time without even thinking about it. You learn how to drive one car, and you can pretty much drive any car, right? You learn the rules of grammar, and you can create sentences you've never heard before. That ability to apply rules to new situations, that is the gold standard of true understanding. And it's exactly what researchers are hunting for in AI. All right, so let's start piecing this puzzle together. First things first, how in the world do you even design a fair test for an AI's ability to think? Well, to get a clean answer, you can't just test an AI on the messy, chaotic internet. You need a controlled laboratory. So that's what the researchers did. They built a kind of digital maze, creating the perfect, isolated environment to run their tests. The experiment itself was pretty elegant. They trained a language model to do just one thing: find the shortest path between 2 points on a map. Think of it just like your GPS finding the quickest route. The AI doesn't actually see a picture of the map, of course. It's all done through text prompts, kind of like what's the shortest path from A to Z. And then the AI has to spit out a sequence of moves, like go north, then east, then south. And here's where it gets really clever. They tested the AI's generalization skills in two very different ways. The first one was called spatial transfer. Basically, can it use what it learned on one map to navigate a totally new map it's never seen before? The second test was length scaling. This was to see if the AI could find a path that was way longer than any of the paths it had practiced on during training. So, what happened when they put the AI to the test? Well, the results were genuinely surprising, and they revealed this really interesting split in what the AI could and could not do. So, the million-dollar question, right? How did the AI actually perform in this maze? Was it a navigation genius, or did it just get completely lost? Okay, check this out. The results showed this shocking split. First, just look at those tall blue bars on the left. That's the AI's performance on brand new maps. It's scoring over 90%, a huge success. It really looks like it learned the rules of navigation. But now, follow the graph over to the right of that dotted line. This is where they tested it on longer and longer paths. Do you see how the success rate just completely falls off a cliff? The moment the journey gets longer than what it's seen before, its ability just collapses, and that is the key failure we need to understand. And this is the real heart of the puzzle. Why this bizarre split? I mean, if it truly understands the rules for finding the shortest path, why would a longer journey suddenly cause it to break down? The paper gives this phenomenon a name: recursive instability. Think of it like this. On every single step of a journey, there's a tiny chance the AI might make a mistake. Now, for short trips, that's fine. But on a really long journey, all those tiny chances of error start to compound. They build on each other like a snowball rolling downhill until a mistake becomes almost inevitable. So it's not that the problem is actually harder, it's that the AI can't perfectly apply its own logic over and over again. And this really hammers home the paper's first big takeaway. Yeah, the models can show signs of true generalization, transferring skills to new places, but they just don't have the stability to apply those exact same skills over longer and longer problems. This result led the researchers to dig into the training data itself. What kind of study material actually works best for an AI? This chart gives us our first clue. Along the bottom, you have the number of unique questions the AI was trained on. And look at how all the lines just shoot steeply upwards, and then plateau. It shows that as you give the AI more unique problems, more variety, its success rate shoots up to over 90%. Variety is what seems to matter most. And clue number 2 digs even deeper. This heat map shows us what's more important. So coverage, going up to side, means seeing more of the map's different locations. Diversity, along the bottom, means seeing more paths between the same few locations. Now just look at the colors. Dark blue is a low success rate, and bright red is a high success rate. Notice how you get to red much faster by going up, increasing coverage, than by going across, increasing diversity? The takeaway is crystal clear. It's better to show the AI a little bit of everything than a whole lot of just a few things. So the lesson from all this data is pretty simple, but it's really powerful. If you want an AI to truly learn a rule that it can generalize, it needs breadth over depth. It has to see that rule applied in as many different contexts as you can possibly show it. They also tried out different training methods. So on the left, you've got supervised fine-tuning, or SFT. You can basically think of this as the AI learning from a textbook with all the correct answers. But notice how its performance peaks early and then actually gets worse? It's like it's overstudying and just memorizing things. Now on the right is reinforcement learning, or RL. This is more like learning from trial and error. And look how much more stable those lines are. But, and this is a big but, RL never gets better than the best SFT model's peak performance. And that leads to another crucial takeaway here. Reinforcement learning is great for making the model more stable and stopping it from overfitting, but it doesn't actually teach it any new tricks. The AI's maximum potential, its performance ceiling, is always set by what it initially learned from that textbook, from its SFT training. Now, any good piece of science is honest about its own limits. So let's take a quick look at the fine print and what the researchers themselves say this study did not cover. Yeah, the authors are super clear about the trade-offs they made. First, this whole thing was a highly controlled synthetic environment. It's not the complex, messy, real world of human language. And second, they used smaller, custom-built models so they could really interpret the results, not massive ones like GPT-4. The goal here was clarity and control, not just trying to get the highest score. So what's the final verdict here? Do these findings from a simple digital maze actually mean anything for the real world? Well, to find out, they applied the exact same principle to a real-world task, solving math problems. Let's look at the table. Just compare the middle column, high coverage, which means a wider variety of problems, to the standard model column. The scores are consistently higher. And for the medium and hard problems, that high coverage strategy is the clear winner. The principle holds up. Breadth really does beat depth. And that brings us right to the core conclusion of this entire paper. An AI's ability to truly generalize, to think systematically, isn't some kind of magical property that just appears out of nowhere. It is a direct reflection of the breadth and the quality of its training data. If we want to build smarter AI, we have to be smarter about the data we feed them. Which leaves us with a final, kind of provocative thought to chew on. If an AI's intelligence is simply a reflection of the data we show it, is it truly learning to think, or is it just becoming a more and more perfect mirror of us? Something to think about. Thanks so much for tuning in to Pod 4 Journal Club.